Today, we will deal with a particular class of polynomial, partially scattered linearized polynomial, and their connection with some geometrical object, linear set, and some objects of the coding theory, rank metric codes. So this is a work, this is a paper already published with Corrado Zanella. So first of all, I will introduce the linearized polynomials over a finite field of order q power n. So they are polynomial of this shape only with the q powers of x. So they set the polynomial until the q degree, they are also called the q polynomials over finite field of order q power n. Of course, q is a prime power. And so this set is isomorphic as an algebra to the set of the endomorphism of fq power n seen as a vector space over fq. And there are the fq linear maps of fq power n. So in particular, in this class of polynomials, there are the scattered ones. And so a q polynomial, a linearized polynomial, is called scattered if this equality holds, imply that y and z are fq linearly dependent. So there are a lot of connections in geometry, in finite geometry, of course, and so a lot of main application. But the most explored in these days, in these years, is this one. So the connection before, we have the scattered linearized sets of the projective line, scattered subspaces inside a projective space, Rayleigh blocking set inside a projective plane. And so the main application found by Shiki in 2016 is the application in rank distance codes. So now I have to introduce here the geometrical objects, the linear sets. And so here we are in a projective space over the finite field coordinated over the finite field fq power n of dimension r-1. And so it is the set of lattice of the vector space fq power n power r over fq power n. And so a linear set is a subset of this projective space such that the vectors here are all in the same vector space U, a vector space m-dimensional, and for this reason the linear set is called has the rank m. So the sides, of course, it is very simple to see that the sides of L is at most this number. And so if U is scattered, if the sides of L is exactly this number. Another way to see U scattered, and of course also the linear set associated with, we have that when we have a projective geometry of this dimension, so the subspace over fq power n can be seen also as a vector space over fq. And so we have a link between this projective space here of dimension r-1 in this projective space with dimension r times n-1. And so the set of points here become a set of n-1 dimensional projective subspaces. And so this set is called the normal n-1 spread of this projective space. And so U is scattered, is a scattered subspace also, of course, with respect to this spread, if the dimension over fq, a vector dimension of this intersection, is at most 1 for any v in fq power n. So the maximum dimension of a subspace scattered is the maximum rank of the subspace, and it depends, of course, of R and N, and U becomes a maximum scattered subspace if, of course, it is scattered, and if any n+1 dimensional vector subspace here is not scattered, of course, with respect to this normal spread. So when we have a maximum scattered subspace, the linear set associated with is, of course, a maximum scattered linear set of PGR -1 q power n. A particular linear set is the subgeometry or canonical subgeometry of this space, and it is a linear set of rank R, exactly the number here, and the projective span of the subgeometry is the whole space. Now we will see the link between maximum scattered linear set and scattered polynomials. So here we are in the projective line, and so the maximum rank for a linear set is exactly n for some result of Blockhaus and Lavrov. And so up to collineation, so we can always suppose that the point 0,1 of the line pg1q power n is not inside this linear set. And so the subspace underlying this linear set becomes of this shape, and also the linear set becomes of this shape, the couple x and f of x. And so it is very simple to see that LF is scattered, and also, of course, the subspace underlying is if and only if f of x is a scattered polynomial. Now, with Corrado, we weaken the property to be scattered, introducing the partially scatteredness of Q polynomials. So if we have this polynomial, we suppose that n here is the product of two integers t and t prime, of course not 0 and not 1, and we introduce these two definitions. The first one, the LQ power t partially scattered, so f of x is a Q polynomial, not a Q power t, of course, otherwise it is trivial, this definition. So it is a Q polynomial such that if this equality holds, this property here implies that y and z are fq power t linear dependent. And LQ power t partially scattered, if this condition holds, we have that y and z are in FQ. Of course, a polynomial is scattered if and only if it is both L and R Q power t partially scattered. So it is a sort of left and right partially scatteredness. So the first one theorem, the first result is we have a subspace of dimension n. And so, of course, we have these three sets. The first one, U tilde, is an n-1 dimensional subspace of this projective space. Rf is an FQ linear set of rank n in this projective space, so coordinated over Q power t. And LF is a linear set of the line. And so in this case, we have that the size of RF and LF is exactly the same if and only if f of x is LQ power t partially scattered. RF is scattered, of course, of rank n if and only if f of x is RQ power t partially scattered, and then if t is equal to f of x is RQ square partially scattered, Rf is a canonical FQ subgeometry of this space. So we obtain these three sets through the FQ linear representation that I explained before. Indeed, we have LF, a linear set in the projective line. We can obtain, thanks because of the map before, the linear set here, RF, and then a projective subspace here in this projective space. So now we want to see some algebraic, very simple properties. So the first one, we can consider for any row, we can consider this polynomial when we have a Q polynomial. Of course, it is still an FQ polynomial. The first proposition is we have f of x a Q polynomial. It is RQ power t, LQ power t, or scattered if and only if this map for any row inside this set, the second set fq power n minus fqt, or fq power n minus fq, this map is bijective. So it is a very, very simple trivial result from the definition that we made before. So another very simple proposition is that if the greater common divisor between t and t prime is 1, any LQ power t partially scattered is also an RQ power t prime partially scattered. Now we want to construct some partially scattered polynomials from others. So, for example, this proposition is very trivial to show that when we have a scattered polynomial, many people among you know this fact, when we have a scattered polynomial, so the sum between a scattered polynomial and a monomial of the type m times x is still scattered. This property holds also for LQ power t partially scattered. And for RQ power t partially scattered, the fact becomes very interesting. Because if we have a RQ power t partially scattered, also the sum between f of x and a q power t polynomial is RQ power t partially scattered as well. And so also polynomial of this type Q power t from a RQ power t partially scattered, it continues to be a partially scattered RQ power t. And so also if we have a Q power t polynomial of this type, and we have a RQ power t partially scattered Q polynomial phi of x, the composition between G of A, A and phi is RQ power t partially scattered if and only if J of A is bijective. So from a RQ power t partially scattered Q polynomial, we can construct other families of this type, of this shape, with this property. And also, if we have n and S, a divisor of n, if this hypothesis holds, we have that the composition of GA of this type and with the monomial xq power s is both LQ power t and RQ power s, Q polynomial. So now we want to see if there exists this sort of polynomial, and so we construct some examples, some classes, some families of these polynomials. First of all, I have to recall the notion of trace of norm of the finite field Q of order Q power m over Q power L. Of course, L is the divisor of m. There are these two functions. And so the first one proposition, and so the first example is a generalization of binomial of the Lunardon-Polverino binomial. So here we have this binomial. If the norm of Q power 2 times t over Q power t is not 1, so f of x is RQ power t partially scattered. Inside this family of polynomials, of course, there are the Lunardon-Polverino scattered polynomial. So here, while here we have always the same polynomial, but now the norm is 1. So this polynomial, it cannot be scattered, but it is LQ power t partially scattered. It cannot be scattered because Corrado Zanella showed that if the norm is 1, norm over Q, not over Q power t, so this polynomial cannot be scattered. But it is
5 minutes.
LQ power t. What?
5 minutes left.
Okay, so now I'll show, yes, this another polynomials. These polynomials contain the family of Marino, Montanucci, and Zullo. And so the last one, our family where there are the scattered polynomials that we found with Corrado in 2020. So now I want to show you the rank distance code. And so this sort of polynomial are linked to rank distance codes. A rank distance code is a subset of matrices, but we can see also this set in setting of the FQ polynomial. And so we obtain some result of this sort with this polynomial. So if f of x is an RQ power t partially scattered, so we have that the kernel has some property, so it is scattered, the dimension is at most n half 2, and then the important theorem is that if we have an RQ power t partially scattered polynomial here, this code is a code, a square code, and it is an S almost an MRD code in FQ power n times n. And so, also, this is the main result about the coding theory object. So if we have this subspace, this is a MRD code, a code of matrices in the setting of polynomial. And so if we have f of x this polynomial and we take the restriction over fq power t, we obtain an MRD code with this parameter, a rectangular MRD code. So if t is equal to t prime is equal to, we obtain a square MRD code, but it is not new. But we don't know if this code is new or is some section, some puncturing of MRD code square. So we study also this sort of RQ power t polynomial, and we study that if j of e is a bijective q power t polynomial and we take the composition of this sort, we obtain that the right idealizer of this code, the right idealizer is a set where when we take the product on the right with the function, with the code word of this code, we obtain that this is always a field, and here it is the field fq power t. So I hope that I was clear, and so thank you for your attention.